Good morning. Welcome to the live session. This is the extra session for the NPTEL course, Basic Environmental Engineering and Pollution Abatement. We will start the session, let others join later. I hope I am audible and the screen is visible. Can you please confirm? Okay. We'll start the session. So this is the extra session for this course, Basic Environmental Engineering and Pollution Abatement. I'm Mahalakshmi S, Research Scholar from National Institute of Technology, Trichy. So this is the general information that this live session will happen every Saturday from 3 p.m. to 5 p.m. I will be handling this session. Today is the extra session, so it is organized at this time. You can use the same Gmeet link to attend the Saturday classes. It is NDA, VDCP, NCG, and all the live session videos are recorded and uploaded on the YouTube channel name Mahalakshmi S. You can find it through at Mahalakshmi Shekhar NIT-Trichy. So now in this extra session, we will see the overview of the lectures completed so far. Like from lecture 1 to 10, we have 10-week lectures. We will discuss the overview of this 10-week course and we will solve the representative problems from each and every week. We will discuss the formulas and some important problems solved in the assignment solutions will be discussed here again. So it is basically the summarization of the whole 10 weeks. So now coming to the week one lecture, uh, it is generally the introduction about this course, like what is environment and its component. So environment is composed of both the living and non-living matters, right? So this component include the abiotic and biotic component. So in the abiotic component, it includes the all non-living organism and then like soil, land, water, all these air, all these components will be coming under the abiotic component. And in the biotic component, if you see, it includes the living organism like human beings, animals, plants as well. Okay, so it is the introduction to this course. So environmental pollution and sustainability. So in this case, it is briefly discussed about how the air, water, and land are all polluted. Voice is not clear. Okay. Wait a minute. I hope it will be audible now and it will be clear. Uh, so this environmental pollution is about the air, water, and land pollution. How the different components of the environment are getting polluted, and sustainability is very important topic to study because what sustainability itself mean is it is that we should consume all the resources present in the earth for us also, and these resources should be available in the same quantity and quality for the future generation. So it is the way, sustainable way to utilize the resources available in the earth. So this is what the sustainability is about. We have to preserve the existing resources. We can consume it, but we should also preserve it for the future generation. I hope it is clear now. Is it okay? Okay. So now in the next lecture, it is about the ecology, environment, and biodiversity. So the ecology is the ecosystem which has different components. We have seen the pyramid. So So we have seen the ecological pyramid, from which we have seen from bottom to top, we have the lower to higher end organism, like the primary consumers, secondary consumers, and tertiary consumers. We have seen all those things. And now coming to the food chain and food web, it is very important since each and every organism is interdependent, the animals eat the plant and the lower end animals will be eaten by the higher animals, like the frogs will be eaten by the snakes and snakes by the other animals. Like this, it goes on. So this food chain is also important, and food web is the complete circle where each and every organism is interdependent. Finally, when these or all these organisms are dying, all these dead organisms will be decayed in the soil itself, and it again goes as the nutrient to the plant. So it goes back to where it all gets started. So it is the food web. Okay. So now next topic is stability and biodiversity of the ecosystem. The stability is very important. Like whenever the ecosystem is getting affected, so how long this ecosystem is going to take to retain its original position? Like it can be a man-made renovation reclamation, or it can be a natural reclamation. So if naturally the ecosystem is healing by itself, then it will take a longer period of time. Man-made reclamation involves the reforestation, afforestation, all these methods. But the natural process is very slow, but by naturally also it can heal by itself. And biodiversity of the ecosystem, this is like different organisms together or living in this environment, right? It is what talking about the biodiversity. And now coming to the ecosystem services and its risk. So what could be the risk posed to the ecosystem means absolutely the man-made activities. It is going to cause the major change in the environment. So that is causing the potential risk to the environment. So one of the major reason is the man-made activity, which is also called as the anthropogenic activities. Another one is the natural activity, like the natural soil erosion, volcanic destruction. All these can pollute the air, atmosphere, but also the water resources, land resources. Everything can also be affected naturally. But major cause is because of the man-made activities. So the risk include the inferior quality of resources. So here inferior quality means deterioration of the existing quality of water, air, and soil. Okay, how all these quality of the environmental components are getting decreased. That is what discussed here. And then risk due to the conservative nature of pollutant. Like we have different kind of pollutant, gaseous pollutant, which is affecting the atmosphere, air, and then the liquid pollutants, which is being discharged into the water bodies, affecting the water, and then the solid pollutants. So solid pollutants are again going to contaminate the soil. So land pollution are all occurred. Okay. So risk due to transmission of diseases. This is another type, right? We have various diseases like dengue, malaria, and then now recently we got COVID. So all these diseases are also possessing a major risk to the ecosystem services. So when these risks are at the higher rate, the ecosystem will not attain the stability so soon. Okay, it will take a longer period of time to get back to its original state. Now the ecosystem services and its risk, part 2. This lecture of the week 1 explains about the type of risk and the hazards. So hazardous components are all described. How these hazards are caused by different components. Like different components are explained in this, and risk analysis. So there is a stepwise process, right? First, we have to identify what type of risk it is, how this risk is caused. So what component is responsible for this type of risk, and what type of hazard, whether it is a physical hazard or chemical hazard or biological hazard. So this type of analysis are done in the risk analysis. Then people will discuss about the management. So how we can manage the risk, what kind of activities or prevention and control measures can be taken. All these comes under the risk management. And then finally, the finalized method to overcome the risk is communicated to the public after the decision taken by the authorities. So this is what discussed in this lecture. So in this one, if you say we have problems based on the bioconcentration factor, so it is nothing but how much amount of the particular pollutant is present in the living organism divided by the how much amount of the pollutant, that is the concentration of X. X here is the pollutant, okay? So X is the pollutant, how much amount of pollutant is present in the environment. The ratio of the existence of pollutant in the organism to the environment is called as the bioconcentration factor. So this is what BCF is about. And then in the risk analysis, we have a problem based upon the intake rate. So I is equal to CE into RI into EF into ED whole divided by BW into AT. So here I is the intake rate of the particular pollutant. It is calculated in terms of milligram per kilogram day, and the C is the exposure concentration. So how much concentration this pollutant we are getting exposed is the CE. And RI is the intake rate, at what rate we are taking. And this is the amount, this is the rate. Okay. And EF is the exposure frequency. How often we are getting exposed to it. Like in a year, how many days we are getting exposed. And ED is the exposure duration. So in a day when we are getting exposed, so how long, like this, how many years we are getting exposed. That is what ED is about. And BW is the body mass. So this body mass is the average adult body mass. It is usually 70 kg. Okay, and then 80 is the averaging time. So this is the time taken. So it is generally taken as 365 days, which is 1 year. Okay. So when we are analyzing the risk, this risk is again classified into two types. One is carcinogenic. We know what is carcinogenic, right? What is carcinogenic? So carcinogenic is a substance which is able to cause cancer, mutation in the people, right? So carcinogenic and non-carcinogenic are the two types of risk. Based upon that, we have different methods to do calculation. In case of carcinogenic, we will take the slope factor to do the calculation. And in the case of non-carcinogenic, we will go for the RFT method, okay, which is nothing but the reference dosage. This is how the risk is calculated. So we will see that in the problem. Now this is one problem from the week 1 lecture. So the question is, if a amount X, if a compound X has a octane water partitioning coefficient of 130. So the octane water partitioning coefficient is 130, and the concentration of X in the lake water is zero point 0.5 mg per liter. So the concentration in the lake water here is the environment. Okay. So the concentration of the pollutant in environment is given as 0.5 mg per liter. Find an approximate concentration of X in the animal at the bottom of all food chain in the lake. So the question asked this is explaining about the lake. Okay, this is the lake. So in this lake, totally the concentration of the particular pollutant is 0.5 mg per liter. Okay, we have different organisms in this lake, including the plants, and then we have fishes, right? So lot of animals will be there. They are asking about the bottom of all food chain, means to the lowest part of the ecosystem. Whatever animal is there, what would be the concentration they are asking to all the living organisms in the lake system. So we have to calculate this concentration X in the animals. we know that BCF is equal to, so BCF is the bio concentration factor, right? BCF is the X concentration in the organism, okay, and X concentration in the environment. This is the formula. Okay. Now we know the X concentration in the environment and X concentration in the organism is the asked. For that, we should know the another unknown parameter BCF. Okay. If we know the BCF value, we can calculate the X concentration in the organism. To find the BCF only, in the question itself, one more data is given, which is nothing but the partition coefficient of octane and water. Okay. So this partition coefficient can be used to find the BCF. So this is the solution. Like we have one more formula. So this is the formula. You have to note it down. So log BCF is equal to 0.79 log of KOW minus zero point 0.4. So here K is the partition coefficient. It is OW because it is the partition coefficient of octane and water. If the partition coefficient is given for any other compound solution, means you can substitute whatever K given in the question here. Just substitute the K value here, which is 130. Now take the log of 130 and then multiply the log of 130 with 0.79, then subtract it with 0.4. Okay. Now we will obtain the log BCF value. So log BCF values, you can substitute the values now. So log of 130 into 0.79 minus 0.4 is nothing but 1.28. Okay. 27. Yes, it is 1.27. Then we have to find the BCF from this value. So how to find the BCF value from the log BCF? Just take the to cancel the log, take 10 power 1.27. Okay. So BCF is equal to 10 power 1.27. So which is nothing but 18.62 liter per kg. This is how the BCF is calculated. Now you know the BCF value and the concentration of X in the lake system, which is nothing but 0.5 mg per liter substituted. So multiply the 0.5 into 18.62. So if you multiply this, you will obtain the value 9.30 something. So if you round off this, you will obtain 9.31 mg per kg. Okay, this is how the unknown concentration in any organism is found. If the value of BCF itself is given and the value of concentration of X in the environment system is given, it is very simple. We can multiply the BCF into the concentration X in the environment to find the concentration of X in organism. Okay. So with this formula, with the given data, you can find any unknown parameter. I hope it is clear. Any doubt in this problem? Shall I proceed? Okay. If you have any doubts, you can ask in between. So now the next question is, so this is about the one of the problems from risk analysis. We will see the two types of problem. When the risk is non-carcinogen, we have one type. When the risk is carcinogen, we have another type. Okay. So first is the non-carcinogenic based problem. The question is when chlorine is used for disinfection of drinking water, chloroform can be produced by reaction of chlorine with residual organics in the water. Estimate the ingestion intake rate for non-carcinogenic effect on an adult resident in a home receiving tap water with an average chloroform concentration 75 microgram per liter. What is the risk? Oral RFT of chloroform is 0.010 mg per kg day. Okay. What this question is talking about is we know that we are obtaining the drinking water to our home through the pipes. Okay. Through public water pipes, we are assessing the water. So how this water is coming to the public tap? So it is coming after the treatment. So in the treatment after primary, secondary and tertiary treatment for disinfection, they are using the chlorine. So chlorine is a chemical which is used to disinfect the water, okay, to kill the microorganisms. So now when this chlorine is in excess amount, what happens when the treatment is also not efficient with a residual amount of organic content in the water, this chlorine will start reacting. Okay. So what happens? This organic matter is composed of carbon, hydrogen and nitrogen. Okay. With the chlorine and oxygen. So with the chlorine, when it is getting reacted, it is going to form a chloroform. We know that chloroform is a not, it is not a carcinogen, but it is not a good one to inhale, right? So it is somewhat having the hazard to the human health. Okay, so it is a hazardous component, hazard agent. Okay, now what the question is about is this chloroform is getting produced by the reaction of chlorine and the residual organic. Now this chloroform, when we are receiving the tap water, is ingested. Ingested means it is intaken by the adult residents. Okay, with an average chloroform concentration. So in 1 liter of tap water, 75 microgram of chloroform concentration is there. So how much they are ingesting, they are asking. What is the intake rate? So we know to find the intake rate, the formula, to find the intake rate, the formula is I is equal to CE into Ri into EF into ED whole divided by VW into AT. With this formula, we can find the ingestion rate. Okay. Then they are asking, the second question is what is the risk? They are asking whether it is acceptable or non-acceptable. I have already said that if the question is about the non-carcinogenic hazardous agent, we have to use the value RFT, reference standard dosage, to calculate the amount of risk. Okay. If it is about the carcinogen, we have to use the slope factor to find the amount of risk. Now we will solve this one. So in the given question, it is mentioned that the concentration is 75 microgram. So it is a mistake if you substitute the 75 microgram. So this is 0.075, okay, not 65. So this microgram per liter is converted to mg per liter. So it is written as 0.075. And then we are converting, now we have to substitute this Ra. So Ra is, uh, 1 minute. The ingestion rate in oral form is given. So this data is missing. 2 liters per day. So now we have to convert this days to years. Okay. So substitute the EF here. In a year, 350 days are here. ED is the exposure duration. It is for 30 years. How this 350 and 30 are taken means it is a standard one. Okay. We have to take 350 days per year and 30 years as standard. When this question is not given in the when this data is not given in the question for the non-carcinogenic, just assume that EF exposure frequency as 350 days and the exposure duration as 30 years. Okay, this will not be given sometimes. Now the body mass weight is again 70 kg. Okay, so it is 70 kg and 80. The duration is, so this is the time taken. This should be considered as 365 days, entire days in the year for 30 years. Okay, so if we solve this one, you will obtain 1.8 into 10 power minus 3 mg per kg day. Now, what you have to find is to find whether this risk is acceptable or not. You have to find the term called hazardous quotient. So, this hazardous quotient is obtained by dividing the intake rate with the reference standard dosage. So, the reference standard dosage is given in the question, which is nothing but 0.01 mg per kg day. And this I value is now found as 1.8 into 10 power minus 3 mg per kg day. So if you divide this one, you will obtain the HQ value. Find this one. So 1.8 into 10 power minus 3. So whole divided by 0.01. It is nothing but 0.18. Okay. So this HQ is less than 1. So we conclude that this level of chloroform constitutes an acceptable risk. So always this HQ should be less than 1. If it is less than 1, then it is acceptable. Okay. This is the condition. If they are asking you about what is the risk, then you have to find whether it is acceptable or not. So this risk is acceptable. It is within the range of 1. Okay, this is how you have to solve for the non-carcinogenic based problems. So in case of carcinogen, this is another type of example. Like if benzene, a known carcinogen, is found in air at a constant concentration of 1 microgram per meter cube. Calculate the risk for exposure to this benzene for an average adult who inhales 20 meter cube per day. So here 20 meter cube per day is the rate of intake given, and 1 microgram per meter cube is the concentration of the benzene present in the air. Note down, it is a carcinogen based problem. Okay. Calculate the risk for exposure to this benzene for an average adult who inhales the 20 meter cube per day with 50% absorption for a lifetime. So they have given that 1 microgram per meter cube is the amount of benzene existing in air, and the adult is inhaling at the rate 20 meter cube per day, but 50 percentage is only absorbed by him, not the entire 100 percentage. Okay. And then one more data given is the benzene slope factor. See, it is a carcinogen based problem. They have given you the slope factor to identify the amount of risk. Okay. So now use the same formula. I is equal to CE into RI into AF into AD whole divided by BW into AT. Now CE is the concentration of our hazardous agent, which is 1 microgram per meter cube. Now only 50 percentage of it only absorbed, not the entire 1 microgram. So 50 percentage means multiply it with 50 by 100. It is nothing but 0.5. Okay. Now they have converted the microgram to milligram. So divide it with 1000 and then substitute 20 meter cube per day, which is the RI value given in the question. So substitute 20 meter cube per day. And here EF and ED take it as 350 day per year. And then for ED it is 70 years. Okay. So here it is 30 years and here it is 70 years because it is the data you should take for the carcinogen. Okay, these are all standard values you have to note down. And then substitute the value of BW and ET. BW will not change. So average adult body weight is 70 kg and AT is again 365 days per year into 70 years. Okay. So now with this we will calculate the I value, which is 1.37 into 10 power minus 4 mg per kg day. Now you have calculated the I. In the case of non-carcinogenic agent, you will find it by HQ is equal to I divided by RFP. This is the formula. Okay. But in the case of hazardous agent, the formula is LCR is equal to I into slope factor. Here you have to multiply the I with the slope factor. There you have to divide the I with the reference dosage. Okay. So what is the slope factor? 0.015 mg per kg day whole inverse. So substitute it here. You will obtain 2 into 2.06 into 10 power minus 6. Here the limit is it should be less than 1. Here the limit is it should be less than 10 power minus 6. Okay, keep this in mind. So this is the one you have to keep in mind always to solve this kind of problem. So this is greater than 10 power minus 6, so the risk is unacceptable. Okay. Shall we move on to the week 2 content? Any doubts? 70 kg. Yes, 70 kg is the body mass weight, average adult weight. We have to take to this to solve the problem. Okay, it is an assumption. Okay. So in this problem, all the data will be given. Only thing is you have to keep in mind that 70 kg is the body mass weight of the adult. And here in the case of non-carcinogen, take EFS 350 day per year and EDS 30 years. But in the case of carcinogen, take EFS 350 day per year and EDS 70 years. Okay. We have to use slope factor for the carcinogen and we have to use the RFD value to solve the non-carcinogen. Coming to the week 2 lecture, it is about the different types of pollution and its sources. We know that there are where you have equated 75 micron. Which one you are asking? 75 micron? Ah, this is the mistake. Okay, so in the question it is mentioned as 75 and here it is substituted as 0.065. But here you have to substitute 0.075 only. Okay, not 65. If you substitute 0.075, it is 1.8 into 10 power minus 3 only. The answer is correct. Okay. Okay. We'll move on to the week 2 problem. So now in the week 2, it is about the different type of pollution and its sources, how these pollutants are released from the industries, and how these pollutants are having the impact over the environmental components like air, water, soil. And then the transmission of pollutants in the environment. It is about the next two lecture, like how the air pollutants are transmitted, how it is dispersed. We have seen the different modes of this air pollutant dispersion. And then coming to the water pollution, how the water pollutants are dispersed, how these are getting penetrated to the groundwater and surface water. These are all discussed in the week 2. Now we have the problems based on the carboxyhemoglobin. So this carboxyhemoglobin percentages can be obtained using this equation, which is percentage COHP is equal to beta into 1 minus e power minus gamma t into CO. So here CO is the carbon monoxide concentration, which will be given in ppm in the question, and the gamma is constant, which is 0.402 per hour, and beta is 0.15 percentage per ppm of CO, and T is the exposure time in hours. Okay. And then we have the air dispersion based problem. In this one, we use the Holland formula, which is delta H is equal to Vs by U T into 1.5 plus 2.68 into 10 power minus 2. Here P is the pressure and D is the diameter, stack diameter, and Vs is again the stack flue gas velocity, and U is the wind speed, and Ts minus Ta, it is the stack gas temperature and ambient air temperature, and again here D is the diameter. Okay, so we use these two formulas. We have problems based on this. Now we will see a problem based upon the stoichiometry. Okay, so to find out the air to fuel ratio required for the complete combustion of the fuel C6H13. So C6H13 is the fuel we are going to use. So with this we are going to supply the air. Okay, so air is supplied. So what is the ultimate product obtained after the combustion? We will obtain the carbon dioxide and we will obtain the water molecules, and then you will obtain the in a air. So air is composed of oxygen, comma nitrogen, right? So one more product is the inert nitrogen. So amount of and reactant nitrogen. Okay, this is the reactant. This is the product we are going to obtain when we are doing the complete combustion. So here to find the air to fuel ratio, the formula is mass of the air required for the complete combustion of fuel divided by the mass of the fuel. For that, you should find how many moles of oxygen is required and how many moles of nitrogen is required to completely combust the C6H13 fuel. Okay. So here there are 13 hydrogen molecules. So all of these hydrogen are going to be formed as the water. So H2O is going to be formed. So 6.5 into 2 is 30. So substitute 6.5 here. Now C6. 6 carbon is there in the fuel. So all the 6 carbon is going to be formed as the carbon dioxide. Now calculate the amount of oxygen required. C into, sorry, 6 into 2 is 12 and again 6.5 into 2 is um, 40, 30. Okay. So this is how we have to calculate. So substitute that here it is in the terms of O2. So we require 9.25 moles of oxygen. The same same moles is required for N2 also. But if you have to calculate the amount of N2 in it, then you know the volume percentage of the nitrogen and oxygen in the air. So in 100 percentage air, we have only 78 percentage of nitrogen, 21 percentage of oxygen. So just multiply it with 78 by 21, then solve this one totally to solve it further. Now we have to calculate the mass of the air required. So in the air, oxygen as well as nitrogen is there. So it is 9.25 and the molecular weight of oxygen is 32. 16 into 2 is 32. And then if you multiply the 78 divided by 21 into 9.25, you will obtain 34.35 and the molecular weight of nitrogen is 28. Okay, whole divided by mass of the fuel. So to calculate the mass of the fuel, it is 6 into 12, which is the atomic weight of carbon, and 13 into 1, which is the atomic weight of hydrogen. So if you solve this one, you obtain the value of 14.8. So 14.8 is the right answer, which is the air to fuel ratio. Okay. I hope it is clear. Any doubt? Okay. Now, now the next problem is about the air pollution. So, this is a very simple problem using the Holland formula. I will read the question. Carbon dioxide is emitted from 75-meter high industrial chimney of diameter. So here this height is given. So the diameter of the chimney is 0.25 to the atmosphere on a clear summer day at the pressure 1 bar. Okay. Wind speed at 10-meter height from the ground is 4 meter per second. Okay. So from the ground it is a 10-meter height. Uh, so at the 10-meter height, the wind velocity is given. But at the height of 75 meter, you only have to find it. Now calculate the effective stack height. So effective stack height is to be calculated. That is the question. Assume B category stability and P value is taken as 0.15 and the stack gas velocity is 7.5 meter per second and the temperature of stack gas and ambient temperature. So again at 80 meter height the stack gas temperature is given. So this is the Ts and then this is the ambient temperature Ta. Okay, and stack gas velocity is given which is nothing but Vs. Okay. Now substitute all the values. So to find the velocity of air at 75 meters, we have to use this formula. Okay, we know all the other values except the wind speed at the 75-meter height. So the height Z2 is 75. At Z1, we know that at 10-meter height, the wind speed is 4 meter per second. So substitute the U1 here. You will obtain U2 as 5.41 meter per second. Now we know all the values. Convert the degree Celsius to Kelvin by adding 273 to it. Okay. Then substitute the values. Now Vs is 7.5 meter per second. It is already given in the question, which is stack gas velocity. And D is the diameter. So the diameter is 0.25 meter and U is just now we have found it 5.41 meter per second. And again 1.5 plus 2.68 into 10 power minus 2. Pressure is 100 kPa. It is given in bar converted to kilopascal. So 1 bar is 100 kPa into subtract the temperatures. Ts is 323 after converting it to Kelvin, and this is not TD, this is TA. So the ambient temperature is 25 plus 273 is 298 divided by 323 into again diameter is 0.25. Okay. If you solve this one, you will obtain the value of 0.537. Now this is the increase in the height. If initially there is a height of 75 meter, there is a height of 75 meter. Just now we have obtained the delta H. Okay. So this is the height H and this is the height delta H, which is nothing but 0.537. Now you have to calculate the effective stack height, which is nothing but H plus delta H. So H plus delta H is nothing but 75 plus 0.537. That is nothing but 75.537. This is how you have to calculate the effective stack height based on the given data. Okay. So now I hope it is clear. We'll move on to week 3 lecture. So the week 3 lectures about the environmental quality standards and to maintain the environmental quantity, we have some standard limits. We have threshold limit for each and every parameter of the air and water, land, everything. Okay, including the noise level also. And we will be using certain instruments to measure the amount of pollutants in these environmental components. That is what this week 3 is about. So initially we have the air quality and standard, and then we have water quality and standard, and the next section in week 3 is about the water quality standards in detail. Like we have different parameters in water quality, like we have pH, and then we have electrical conductivity, then we have the total solid. This total solid is further classified to the suspended solid, dissolved solid, and then volatile solids. So total solids, and then heavy metals in it. Okay, so heavy metals and other important parameter include the including BOD and COD, oxygen demand. So these are all some quality parameters in the case of water, and in the case of air, it is the NOx, SOx emissions in general. Okay. Apart from this, we have the greenhouse gas, carbon dioxide, and carbon monoxide. These are the pollution. How much limit it should be are all discussed here. And in instrumental techniques, we have discussed some electrochemical based estimation thing. And in chromatography, we have discussed about the gas chromatography and liquid chromatography. So in the gas chromatography, only the compounds which are volatile in nature can be measured using the gas chromatography. In the liquid chromatography, we have discussed about the HPLC. So in the HPLC, we have different columns, right? It is the based upon the interaction with the column. So we have different types of columns. Based upon the column, that chromatography types will also differ, like size exclusion chromatography, which is purely based on the size. And then we have ion exchange chromatography, like a cation and anions can be exchanged in the column and particular pollutant can be removed. Reverse phase chromatography. So many different types of chromatographies are there in HPLC. Then we have discussed the instrumental analysis based on the spectroscopic methods. So the spectroscopic methods includes the UV visible spectrophotometer. So this UV visible spectrophotometer The principle behind is the Beer-Lambert's law. So, how much amount of light passed through a particular cuvette is absorbed, and how much is taken by the sample itself. Okay, so this is a color-based method, and how much absorbance is there is directly proportional to the so the absorbance is directly proportional to the particular concentration of the contaminant. Okay, this is how this spectroscopic method works. Now, coming to some sample problems. First question is find out the DO. DO is the dissolved oxygen. Okay, very important parameter of water. So find out the DO in aerated water at 25 degrees Celsius in a treatment plant. The KH of O2 at 25 degrees Celsius is given as 1.3 into 10 power minus 3 molarity per atmosphere. It is a simple problem. We use the Henry's law. So, according to the Henry's law, it is that oxygen concentration is proportional, is given by, okay, nothing but P is proportional to the partial pressure of the oxygen, and this O2 concentration is equated by the Henry's constant. So this Henry's constant will vary based upon the temperature. Okay. So now at 25 degrees Celsius, this Henry's constant is given 1.3 into 10 power minus 3 molarity per atmosphere. Okay. Now you know that partial pressure of the oxygen in the atmosphere is constant, which is nothing but 0.21 atmosphere. With these two data, you can easily find out the concentration of the DO. That is nothing but the oxygen. Okay, so just multiply this KH into PO2. So KH is 1.26 into 10 power minus 3 and O2 is 0.21. Here it is in molarity. We have to convert it to mg per liter. Okay, we know that it is 32 gram per liter, and 1 gram is equal to 10 power 3 mg. So we have multiplied it with 10 power 3 here. So finally you will obtain the value of 8.467 milligrams of oxygen per liter. Okay. Why I am multiplying 32 means? Because it is the molecular weight of the oxygen. 1 molar oxygen is equal to 32 grams per liter. Okay. This is a simple problem. Now we have one more example problem. The concentration of thorium in monazite sand is 0.05 microgram per liter. This is also a simple one. So if you see, the concentration of the pollutant is given in microgram per liter. And how much thorium is present in 100 kg of sand? Here they have given the concentration in per liter, but the amount of the sand is given in kg. Okay, it is very simple if we multiply 100 kg into microgram per liter, but the units are different. So what you have to do is you have to calculate the amount of the sand in terms of volume, that is nothing but liter. We have to convert this kg to liter. So if we have to convert the kg to liter, we have to use the data given called bulk density. So bulk density is nothing but how much amount of the sand is filled in a particular container of a particular volume. Okay. So this is the bulk density. This is how the bulk density is obtained. So we have to use the value of bulk density to calculate the amount of the sand in liters. Okay, this is a simple conversion done here. So 100 kg divided by bulk density. Okay, density is equal to weight by volume. Okay, to find the weight, we have to divide the to find the value or volume, you have to divide the weight with density. So here the bulk density is 1650 kg per meter cube and the weight is 100 kg. Now to convert the meter cube to liter, you have multiplied 1000 liter per meter cube in the numerator. So it is nothing but a simple unit conversion. 1 meter cube is equal to 10 power 3 liters. Okay. Now we have obtained the volume of the 100 kg sand, which is equivalent to 60.61 liters. Now it is very easy to calculate the thorium in the 100 kg of sand. Okay. Now just multiply the concentration 0.05. Here in the question it is given as 0.05. So substitute the value of 0.05 here. So 0.05 into what is the volume? 60.61. Okay. So we will obtain the value of 0.05 into 60.61 is 3.03. So the answer is 3.03 microgram. In the question, if it is given as 0.4 gram, you have to multiply with 0.4 gram. Okay, this is your tutorial solution. Okay. According to the question, substitute the data. So the answer is 3.03 microgram. Is there any doubt in week 3 assignment solution? Shall we move on to week 4? I see no doubts. So coming to the week 4 lectures. So this week 4 is about sampling and characterization. Okay. So what sampling is done means air pollutants. So how these air pollutants are getting sampled? It includes the ambient air sampling and stacked sampling, gas component analysis. What type of contaminants are present in the gas component? And in the next lecture, it is about the water pollutant sampling. So here the how the sampling of polluted water is done and how the parameters like pH, conductivity, and other parameters are measured by using the analytical methods and bacteriological methods. Like we have the weight-based method for the total solid measurement, and we have COD and BOD. Okay, we can measure the dissolved oxygen using the Brinkless method, chemical method, and COD, BOD are all measured with the help of analyzing the amount of DO in it. Same the Winkless method is used. And then the bacteriological measurement includes the measurement of the fecal coliforms in it. Like this is the indicator microorganism. Okay, so it is the indicator microorganism to measure the microbial contamination because most of the wastewater is getting contaminated with the black water. Okay, it is nothing but the drainage water. It contains the human feces. So the E. coli, Escherichia coli is the indicator coliform, which is helpful in measuring the microbial contamination of the water. Now the next one is the solid waste and soil sampling and characterization. So here in this case, solid waste include the biomass. So this biomass is a solid waste. This can be obtained from many different sources, like from agricultural residues or from domestic waste, as municipal solid waste. So all these are the biomass which can be converted into a gaseous fuel and also a solid fuel. Okay, so that is what about the energy content and how this energy content is determined. It is determined by using an instrument called a bomb calorimeter. Okay, so this bomb calorimeter is helpful in finding the calorific value of the particular biomass. So this is one of the method. And then physical and chemical methods includes many methods like cellulose, hemicellulose, that is the lignocellulose content estimation by using the chemical method. And then some other method includes the proximate analysis, where you will calculate the volatile matter. First is the moisture, then volatile matter, and then the fixed carbon, finally the ash content. Like this, you will measure these parameters in the proximate analysis. And then in the ultimate analysis or elemental analysis, the elemental composition is measured, which is nothing but the carbon, hydrogen, nitrogen, sulfur, and then indirectly oxygen content. These are all measured in the ultimate analysis. In the next lecture, it is about the environmental laws and regulatory framework. So here we see different laws and acts and what are the frameworks made to protect the environment, or we'll discuss in the last lecture of week 4. Okay. With this introduction, we will solve few problems from assignment 4. Uh, so the first question is 2 gram of dried agricultural waste. So 2 gram of dried agricultural waste is leached with benzene and ethanol mixture at the ratio 2 is to 1 at 60 degrees Celsius for 3 hours. After leaching, the residue is dried in a hot air oven at 105 degrees Celsius to a constant weight of 1.8 gram. This dried material is put in a flask containing 150 ml of zero point 0.5 normality NaOH solution. The mixture is boiled for 3.5 hours with recycled distilled water. After this, the residue is washed with the distilled water till all the sodium ions are removed and dried to a constant weight of 1.3 gram. Determine the extractives and hemicelluloses content of this waste based on dry basis. If the moisture content of the waste is 15%, determine these values with respect to original sample. So the question is to estimate the amount of extractives and amount of hemicellulose present in the waste. Okay, it is very simple. So in the first step, initially you have 2 grams of waste material, agricultural waste. It is leached with the chemicals, and then after leaching, it is dried. So after the first step, we are having the residual weight of the particular biomass of 1.8 gram. Okay. Then this in after the first stage, we have 1.8 gram. In the second stage, what is happening? So this dried material is treated with the NaOH solution and it is boiled, then recycled with water. Again, after this, the residue is washed and after removal of the sodium ions because we use the NaOH solution. The final weight is 1.3 gram. Okay. So after the first step, it is 1.8 gram. After the second step, it is 1.3 gram. Okay. This is the data you have to keep in mind. So this is the initial mass and this is the M1 and this is the M2. Okay. Weight after the extractive, this is the weight after the hemicellulose separation. Now we have to find the amount of extractive and amount of hemicellulose. For that, you have to use these two formulas. So these two formulas are note on this. It is just subtracting the weight reduction with the initial weight, dividing it with the initial weight, which is nothing but m naught minus m1 divided by m naught into 100. Substitute the values 2 minus 1.8 divided by 2 into 100 is 10 percentage. So in this one, 10 percentage is your extractive content. And then the hemicellulose content is m1 minus m2 whole divided by initial mass m0 into 100. So it is nothing but 1.8 minus 1.3 divided by initial mass is 2, which is nothing but 25 percentage is the hemicellulose content in your agricultural waste. So now you have found the content of extractives and the hemicellulose, but another data given is if the moisture content of the waste is 15 percentage. So here in the waste material of 2 gram, 15 percentage is the moisture. Only 85 percentage of 2 gram is the solid waste. Rest of the weight is because of the 15% moisture content. So just divide the percentage of multiply the percentage with the fraction of 0.85. Okay, 15 percentage is moisture and the 85 percentage is your residue means 100 minus 15 is nothing but 85. Okay, so out of this 10 percentage, 85 percentage is the actual extractive content. So if you multiply it with 0.85, you'll obtain 8.5. So out of the 25 percentage, the actual hemicellulose content is 85 percentage. So multiply it with 0.85, you will obtain 21.25 percentage. Okay, this is a simple problem again. Next, we have a problem based on the proximate analysis. The question is 1 gram of municipal solid waste sample is heated at 105 degrees Celsius for 24 hours. So initial weight is 1 gram. Okay, initially it is 1 gram. So it is dried, and then after the dried material weight is 0.85. So the next weight is 0.85 after drying. Then we are heating it in the furnace at 950 degrees Celsius for 7 minutes in absence of air by putting the lid of the crucible. The weight loss is found to be 0.25 gram. So after heating in the furnace, the weight loss is 0.25 gram. Note down the weight loss only is 0.25 gram, not the remaining weight. So in this one, 0.85 is there. Yeah, the weight loss is given as 0.25. So subtracted 0.85 minus 0.25 is nothing but 0.5. That is the remaining weight after the second step. So when the temperature reaches to the ambient temperature, its lid is open and it is further heated in the oven at 750 degrees Celsius for half an hour in the presence of oxygen. Now in the presence of oxygen, it is again heated. After cooling the material, the residual mass of the material is found as 0.1 gram. This is the final weight left out in the crucible. So after this step, the remaining weight is zero point 0.1 gram. Okay. So determine the moisture, volatile matter, ash, fixed carbon. We should know the order of these one. First, what is get eliminated is the moisture. Then what is getting eliminated is the volatile matter. Then you will have the fixed carbon, and finally you will have the ash cut. So if this 1 gram is taken as the 100 percentage, the amount of moisture removed is 100 minus 85 is 15 percentage. Okay, so that is the amount of moisture removed. Okay, now the amount of volatile matter removed is 0.25 into 100 is nothing but 25 percentage. Then amount of fixed carbon remained here is after the removal of volatile matter you have 0.5 gram, right? So it is 50 percentage. 0.5 into 100 is 50 percentage. And the final weight remaining is the ash content. So 0.1 gram into 100 is 10 percentage. So if we add all these things, we will obtain the total mass of 100 percentage. We can check the answer like this. So 15 plus 25 is 40, 40 plus 50 is 90, 90 plus 10 is 100. So the right answer is 2, option 2. Moisture 15 percentage, volatile matter 25 percentage, fixed carbon 50 percentage, ash content is 10 percentage. Okay. And we have one more problem based upon the bomb calorimeter. So far, do you have any doubt? Shall I proceed? So now the question is to determine the water equivalent of bomb calorimeter. 1.6 gram of benzoic acid sample having the HHV, that is the heating value, 6,318 calories per gram was used. The experiment produced a net corrected temperature rise of 4 degrees Celsius. And then the experiment produced a net corrected temperature rise of 4 degrees Celsius. The acid titration required is 11.9 ml of standard alkali and 8 centimeter of par 45C10 nickel chromium fuse wire was consumed in the firing. Determine the water equivalent of the bomb calorimeter. So how the bomb calorimeter is functioning means we have a bomb inside the water. Okay, it is surrounded by the water. The bomb is surrounded by the water. We will be supplying the oxygen to it so that the combustion process takes place. So now we have a crucible here, and this crucible will be containing the sample, and from this bomb there will be a string. to which our wire is getting connected. Here the nickel chromium fused wire is used. Okay, so because of the oxygen and this contact with the sample by the help of the wire, the combustion takes place. So when this combustion is taking place, what is happening here is temperature rise will happen because this heat is dissipated to the water. Water will absorb the heat. Okay, so there will be an increase in the temperature of the water. This is what happening in the warm calorimeter. Now with these values, we will calculate the data. We will calculate the water equivalent. Okay. So in the question, the given data are H is given as 6318 calories per gram. Okay, and M is mass of the benzoic acid taken is 1.6 gram, and C1 is 11.9 ml, C2 is 0. What does this C1 and C2 means? These are all the correction factors. Okay, C3 is 8 centimeter. I will discuss this later here. And then the temperature rise given is 4 degrees Celsius. So we are going to use this formula. Gross calorific value is equal to T into W minus E1 minus E2 minus E3 whole divided by M. Where here T is the temperature rise and W is the water equivalent of the calorimeter. That is what asked now in the question. Okay. And then E1, E2, E3 are all the correction terms. So E1 is the correction term for the heat of formation of nitric acid. So for this only we are using the titrating agent and the volume is given as 11.9. Okay. So E1 is calculated by E1 is equal to 0.0, E1 is given by 11.9 ml into 1 calories per ml. This is constant. We have to multiply always the given ml of agent, this titration agent used along with the 1 calories per ml. Okay. So 11.9 into 1 is 11.9 and E2 is the correction factor where you have to multiply 13.7 into C2. Okay. This 13.7 is constant and C2 is the concentration of sulfur in it. Okay, here no data is given for sulfur content. Okay, nothing is given about sulfur content. So you can just take this C2 as 0. So this whole E2 term will get eliminated in the calculation. Okay, C2 is 0, so 0 into anything is 0. So E2 is also 0. Now E3 is the correction factor. It is the correction factor for the heat of combustion of the fuse wire. So for this one, the formula is 2.3 into C3. So here the type of wire used is the PAR 45C10 nickel chromium fuse wire. So it is always constant. 2.3 is constant for this type of wire. And C3 is the length of the wire used, which is nothing but 8 centimeter. It is given in the question. Now, if another type of wire, like say for example, we are using the 34 BNS gauge iron fused wire means you have to take this correction term as 2.73, 2.7 into C3. Okay. And if you are using the platinum wire, then you have to take 0. Okay. Totally E3 as 0. So this is the thing you have to keep in mind. Now it is the nickel chromium fuse wire. So 2.3 into C3 you have to take. C3 is the length of the wire used, which is 8 centimeter. If you multiply this one, you will obtain the value of 18.4 calories. Now with this we have E1, E2, E3 and H and also T. Just rearrange this formula and it will be W is equal to H into M plus E1 plus E2 plus E3 divided by T. 6318 is H value, 1.6 is the mass of the sample and 11.9 is E1, E2 is 0, E3 is 18.4 whole divided by 4 degrees Celsius, which is the temperature rise. So the water equivalent is finally obtained with the help of this formula, which is nothing but 2534.1 calorie per degree Celsius. Okay. So you have to use this formula. With the help of this formula, we can find the water equivalent. Okay. If the water equivalent itself is given in the question, then you must be finding the GCV value. Okay. I hope it is clear. Also, I see no comments here. We will proceed to week 5. So the week 5 is about the air pollution control. So now in the air pollution, we have different air pollutant. As I said, mainly the SOx, NOx, and then the carbon dioxide, then the carbon monoxide. Okay, so we have these many pollutants. So now in this one, we have different processes and different equipments to collect the air pollutant. One is the gravity settler. Okay, it's a very simple mechanism. Based upon the gravity, these pollutants are collected. And then in the air pollution control 2 lecture, we have the other equipments like electrostatic precipitator. So you should know this electrostatic precipitator. So there is a charging of this one. Okay, minus 2 plus charging is there. So when the air is passing in this way, these air molecules, initially these air molecules will be having the dust particle like this. Okay, when these dust particles are getting charged when it is passed through the electrostatic plates, what happens here is there will be a collecting plate as well. Okay, so these particles will get charged. Only the clear air will get passed through, and these trapped dust particles will be when decharged, it is collected in the collecting plate here. Okay, this is the collector. This is how the air is getting purified in the electrostatic precipitator. And in the case of fabric filter, it is very simple. As the name indicates, so this is the fabric filter. It have more than 100 filters bags in it. So the air will be passing through in this direction. Like one by one in the filter bags, the air will get passed through. And all the dust particles will be collected at the bottom later. Okay, this is how the fabric filter works. Next is the cyclone separator. So this cyclone separator is a little different from these one. Like we will be having a cyclone separator like this. So based upon the incidence only, like a cyclone will pass down and again it will come up. Okay, base it will the dust particles in the air will get collided against the wall of this cyclone separator. Based upon the impedance only, the solid particles will settle down and the fresh air alone will pass through, and the dust are collected later. Okay, and each and every method is having its own advantage and disadvantage, and each and every method is having its own efficiency in dust removal. Okay, and other types include scrubbers. Scrubbers can be a wet scrubbers. It uses the chemicals and absorption based method. And then all these methods are to control the SOx, NOx, and carbon dioxide emission. And another topic discussed is the air purifier, household air purifier. Okay, so these are the overview of week 5. Now we will solve the problem for the week 5. So in the week 5, the first problem is calculate the plate area of an electrostatic precipitator, removing 85% of the particulate matter from the exit gas of a cement industry having the 200 ppm of particulate matter. So the concentration of the particulate matter is given 200 ppm. And when this particulate matter is passing through this ESP, which is nothing but electrostatic precipitator, initially 100% is there. Okay, Finally, only 15% is left out in the air. Okay, and nearly 85% is captured by the ESP, and the concentration is given as 200 ppm. Now the exit gas flow rate as 150 meter cube per second. This is the flow rate of the exit gas. So it is 150 meter cube per second. This is a flow rate and the drift velocity of the particle. So the drift velocity W of the particle is given as 0.11. Okay. So now we have to substitute all these one in the formula. Collection efficiency is equal to 1 minus e power minus AW by Q. Okay, this is the standard formula with which we can calculate the collection efficiency and with which we can also find the collection area of the plate based upon the given data. Okay, now the question is to find the collection plate area. Okay, efficiency eta is given already as 85. So 85 percentage means 85 by 100, which is nothing but 0.85. Substitute it and again 1 minus e power minus 0.11 is the drift velocity given and A is the area we need to find out, Q is the flow rate. So here the exit gas flow rate is given as 150. So substitute all the values here. Okay, then solve this one to obtain the area of the plate as 2586.98 meters square. Okay, I hope it is clear. You have to take long to cancel the uh, exponential term and you have to solve it. Next problem is, so this is the ESP based problem and this one is a gravity settler based problem. So as I said, gravity settling is a very simple process. The air is passed through a large area having the different mesh. Okay, in the each and every mesh, what happens based upon its size, based upon the gravitational force, these particles will be collected. Okay, so the dust size can be from less than 5 to greater than 70 micron. And then we have the weight percentage of dust collected in each and every chamber. And then what is the fractional efficiency? Its efficiency of collection is also given. Now we have to find the overall collection efficiency. So to find the overall collection efficiency, this is the formula, which is nothing but the total efficiency is equal to summation of the individual weight of the summation of, it is the product of individual weight of the dust particle into its fractional efficiency of the individual dust particle. How it is calculated, I will do a model now. So first the weight per 100 gram of this particle is given. So it is the weight of the particle in each section. If we add this, totally you will get 100. Okay. So now it is 2 out of 100. Okay. 2 is 2 gram of weight per 100 gram of dust particle is collected in the first one. Okay. And its fractional efficiency is given as 1. Okay. Then you have to add it with next portion, which is nothing but 3 by 100. So 3 by 100, multiply it with the respective fractional efficiency, which is nothing but 7. Okay. Then next one. Next one is 10 to 15 micron range of dust particle. So how much amount of particle is separated means efficiency is 20 and the weight is 4. So 4 out of 100 grams is collected here and then its efficiency is 20 percentage. Like this you have to do for all the section. Finally, so you have to continue this. Then finally you have to do for greater than 70 micron particle. So here the weight percentage is 5. So 5 out of 100 is collected into its fractional efficiency is 100. Okay. So if you add everything, you will obtain the value of 80.9 percentage. Okay, this is the right answer. So, any doubt in the week 5 problem? Shall we move on to the week 6? Thus, the value 100 gram is going to remain constant. Yes. So, it is nothing but out of 100. So, out of 100 gram, how many grams are there? Okay, it is the weight percentage. It is weight per 100 gram. So, it is also in percentage. That this is the weight percentage. So, you are dividing each and every respective weight with 100. Okay. Okay. Is it clear? Okay. So, now we will move on to the week 6 lecture. So now we have come to the water pollution based problems. So here the treatment of surface and groundwater for drinking water generation. Okay, so the treatment of surface and groundwater is discussed in this lecture. So the sources of drinking water is mainly the running river water and then some pond reservoirs. These are the sources. And what is the need for the treatment because of the contamination? And how these surface and groundwaters are treated are all discussed in this lecture. And then coming to the treatment of domestic and industrial wastewater. So these are all the running waters, and these are all the domestic and industrial wastewater means from every household waste we are collecting the domestic wastewaters, and the industrial wastewaters are from the industries. Okay, generally these household wastewaters are treated in the STPs, okay? And these industrial wastewaters are treated in the ETPs, which is nothing but effluent treatment plant. So, in the household wastes can be managed by on-site disposal, like in the house itself, or it can be sent to the sewage treatment plant. And in the case of industry, it is going to the effluent treatment plant. And then common effluent treatment plant is nothing but a area having enormous number of industries in it. So commonly these effluents are treated by mixing up. That is where the common effluent treatment plant is coming. Okay. And then in the case of water treatment, we know that different steps are there: primary, secondary, tertiary. Then only finally the wastewater is converted to fresh water. Right. These many steps are there in between the treatment. So in the primary treatment, what is happening? So the primary treatment is basically the removal of the large solid particles just by a sedimentation process, like a physical separation method. So the solid liquid separation is going to happen in the primary treatment. For that, you have a bar rack in between. So initially, the bar racks will be there. You have the bars like this, so the water will be passing through the bars so that lot of solid particles will be separated behind the bars itself. Then comes the grit chamber. So in the grit chamber, it is helpful to control the velocity of the flowing water. Then comes the equalization tank. So here in the equalization tank, we are allowing it to settle down slowly. Okay, then so the water is completely mixed here. Okay, and then the sedimentation tank. So in the sedimentation tank only the gravity based settling is going to happen, so that the solid particles will settle down and only the liquid particles will be floating. And then based upon the type of settling, there are different designs and settlers and floaters are there. These are all discussed in this lecture. Now coming to the secondary treatment process. So this is mainly biological method. The primary is the physical method, and secondary is the biological method. Absolutely, we will use some chemicals also, but mainly we use microorganisms. That's where it is coming the aerobic anaerobic treatment. So in the case of aerobic treatment, the product will be the CO2 and H2, right? But in the case of anaerobic treatment, the product will be methane. Okay. And this is the lagoon. So this is a pond system based treatment. There are different type of lagoons. And this is again the upflow anaerobic treatment process. Then the biofilters like membrane filters are all used in the secondary treatment process. So introduction to primary and secondary treatment was given in this lecture. In detail, it is discussed in the further lecture. So now one of the problem is a circular sedimentation tank fitted with a mechanical sludge removal unit is to treat the 4 million liters of water per day. So the amount of water treated is 4 million liters. The detention time of the tank is 5 hours. The amount of time the water is retaining in the tank is 5 hours, okay, in a day. If the depth of the water is considered to be is restricted to be 4 meter, the depth is 4 meter, calculate the diameter of the tank. You have to find the diameter of the tank. Capacity of the tank can be calculated as, so if you have the equation here, this is the standard equation to find the dimensions. So it is nothing but V is equal to D square into 0.11 plus 0.785 H. 0.11 plus 0.785 H. So now you have to calculate this unknown parameter diameter. Okay. Already the depth of the tank, that is the height, is given as 4 meter. Okay. So now the depth of the tank is given as 4 meter. And then you have the capacity of the tank. Okay. Only thing you have to calculate is the volume of the tank. So how to find the volume of the tank? For that only the data given is the 4 million liters of water are treated per day. So this is the flow rate. Okay, this much of water is treated in a day, and in a day, how much time this water is retaining in the tank is 5 hours. So we have to calculate the quantity of water, that is the capacity of the tank with this data, which is 4 into 10 power 6 into 5 out of 24 hours. It is the detention time. Okay, so in a day, the total capacity is 833 meter cube. Okay, so this is the volume you have to use to calculate the diameter. Now substitute the volume here. 833 is equal to d square is unknown again, and 0.11 plus 0.785 into the height given in this problem is 4 meter. Okay, so substitute 4 here. Okay, now you have to divide this value here. This comes to here in the denominator. Then take the square root of this value to obtain the diameter of the tank. So the right answer is 16 meter. Okay, if you want, I will solve 0.785 into 4 plus 0.11 is 3.25. Okay. So again, 833 divided by answer is 256.3. You take the square root, you'll obtain 16.009, which is nothing but 16 meter. Okay, this is how you have to solve this problem. Now coming to the next problem, this is about the sedimentation tank. Okay, now this is about the continuous flow settling tank. Okay. Here, the question is for a continuous flow settling tank, 3 meter deep, 60 meter long. So here already the dimensions are given. Okay, what would be the flow velocity of the water? Now they are asking you to find the flow velocity of the water by giving the dimension of the tank. Okay, what would be the flow velocity of water for effective removal of 0.025 millimeter particles at 25 degrees Celsius. The specific gravity of the particle is 2.65 and the viscosity of the water may be taken as 0.01 centimeter square per second. Okay. With this data, we have to calculate the flow velocity. So how flow velocity is calculated means for that we have a relation. Okay, V by Vs. Okay, flow velocity by the settling velocity is equal to L by H. Okay, already the length and the height are given. Substituted 60 by 3 meter. Now, how to find the settling velocity of the particle means we have to use this formula. Vs is equal to gdp square into rho p minus rho divided by 18 mu. Now you know the specific gravity of the particle, and the specific gravity of the water is 1, and the diameter of the particle is given as 0.025 millimeter, right? So substituted 0.0025 square because it is converted to centimeter. Okay, so 0.0025 the whole square divided by 18 mu. So here the viscosity is in centimeter, so you are converting the diameter also to centimeter. So 0.01 centimeter square per second is substituted here. So when it is solved, you will obtain 0.0562 centimeter per second. Okay, this is the settling velocity. So substitute the value of Vs here. So V is equal to 60 by 3 whole into this Vs will come here, right? So Vs is 0.0562. So if you solve this, you will obtain the value of 1.125. Okay, centimeter per second. Same as the unit of Vs. Okay, this is the right answer. Is there any doubt in the week 6 lecture? Any doubt? We will move on to week 7 now. So week 7 is about the secondary treatment. Now we have seen about the primary treatment and different tanks used, how the settling and separation are happening. So in the secondary treatment, as I said, the secondary treatment is mainly the biological treatment which uses the microorganism to treat the water. So the first one is the ASP, activated sludge process. So what is ASP? So in the ASP, you have to keep in mind that this incoming wastewater is agitated, okay, is agitated, and then it is produced as the clear water. With the help of one more division here is the settling tank. We have one more settling tank here. Secondary clarifier SC. So what is happening here is the wastewater coming in is extremely agitated. Why this is agitated means to provide enough amount of oxygen, that aeration is happening here. So that by uptaking the oxygen, the organic residues in the wastewater are decomposed, and the product forms are the water and the sludge. So in the secondary settling tank only what happens, the clear water will be on the top and the sludge will be deposited at the bottom. Okay, this is what happened in the secondary settling tank. Then this clear water is taken out, the sludge is sent for the treatment process. This is happening in the ASP. And then the another method is the trickling filter. So this trickling filter is a fixed kind of filter, like so. So this is the type of trickling filter. Here, what is happening means microorganisms are embedded to this filter. Okay, you have the microorganism here, and to this the wastewater is sparged, like it is trickled. So this wastewater is passing through the filter containing the microorganism. Okay. Finally, the clear water will be there collected. Along with this, what happened? The sludges will be formed. How the sludges are formed means these microorganisms will eat the organic content present in the wastewater. That is the substrate for the growth of the microorganism in this filter. Okay. and this will grow up in number, and it will form a slime. Okay, so this will break off, and it will fall. It will break and fall off after some period of time. That is collected as the sludge. Okay, and after taking up the organic content for it to grow, only the clear water is collected from the trickling filter. Okay, this is what happening in the trickling filter. Next, you have the upflow anaerobic sludge blanket reactor. So this is the anaerobic based process. These are all aerobic based process. Here, in the absence of oxygen, we will be decomposing the waste and separating the clear liquid. Okay. Lagoon is again a pond system. It can be anaerobic, it can be aerobic, or it can be facultative. Like it can be aerobic in the top part and anaerobic in the bottom part. It can be a facultative type also. Okay, it is a pond based system. And then we have advanced secondary process. So we have advanced methods involved in the secondary treatment, where we will use the sequential batch reactor. So the sequential batch reactor is somewhat different from the ASB. Okay. So in the ASB, you will be treating the wastewater in a tank, and where it is agitated, then the this output is going to the secondary clarifier. There you will be having the separation of the clear water from the sludge. But the same thing is going to happen here, but it is a sequential batch reactor. So only one tank is used for all the process. First you will be filling up the tank. Okay. First you will be filling up the tank. Then so this tank is completely filled. And then here itself we will be agitating it for some period of time. Aeration will be there, mixing will be there. Then after some period of time, no aeration and no mixing will be there. Okay, so it is getting reacted. After some time, it is getting separated. Okay, you are allowing it to separate in the same tank itself. Then the decant phase will come, where you will collect the water and dispose the sludge. Again, after that, you will fill the same tank, then this process will go in cycle. This is what happening in the sequential batch reactor. The only difference is that all the process are happening in a single reactor. Okay. And granular activated sludge process is a process where you have granules having the microorganism. The inner core is the anaerobic core, and initially you have some oxygen content in the outer layer. When it goes inside, it will be anaerobic. So both aerobic and anaerobic treatment will happen in this granular activated sludge process. Then comes the membrane bioreactors, where the membranes are having the microorganisms um, are there in this MFR, MBR. So when water is passed through this membrane, these microorganisms will take up the organic content and grow in membrane, and only the fresh water will be coming out of the membrane. Okay. And another type of advanced secondary process involves the use of plants. Okay, so phyto means here plants. So plants are used to clear the contaminants in the water. This phytoremediation. So these are taken up by their molecular mechanism. So in the cytoplasm, these contaminants will be used as the growth substrate for the plant. Now, in the term of phycoremediation, here the term phyco means the algae. So you use the algae for treatment of the waste material. So this algae is microalgae, macroalgae. Mostly the microalgae are used. You have different reactors like vertical tubular reactor and then a horizontal tubular reactor. Okay, and there are different methods like open pond system, where you will cultivate this openly in an open environment, and then in the reactors also you will cultivate the algae. So where this algae is clearing the waste matter means, again this algae will also consume the salt present in it, consume the amount of excess carbon nitrogen present in the wastewater will be taken up by the algae for its growth purpose. So all these contaminants are the growth substrate for the microorganism like the algae. Okay, and then this is the overview of the secondary process and secondary treatment equipment. Now we will go to the problem. The question is a complete mixture activated sludge process is used to treat the wastewater flow of 2 mld having the BOD 5 of 250 mg per liter. So here the flow rate Q is given as 2 mld and the BOD 5 value is 250 mg per liter. The biomass concentration in the aeration tank is 2500 mg per liter and the concentration of net biomass leaving the system per day is 70 mg per liter. So you have an activated sludge process. So you have the incoming wastewater of flow rate 2 mld and here during the treatment process the microbial biomass like microorganisms are growing in number, right? So the concentration of microorganism is the MLSS, so which is given as 2500 mg per liter. So X is 2500 mg per liter, that is the MLSS biomass concentration. And then the net concentration of net biomass leaving the system. After the activated sludge process, biomass leaving the system is 70 mg. So 2500 mg per liter is there, and in a liter 70 mg of the biomass is leaving the system. And the capacity of the tank is V is equal to 250 meter cube. They are asking the hydraulic retention time of wastewater in the aeration tank. So in this tank, how long this water is retained, they are asking. Okay, it is very simple. The formula is HRT is equal to V by Q. V is the volume of tank which is given as 250 meter cube. Okay, and Q is the flow rate. 2 million liter, 1 million is 10 power 6. So it is 10 power 6 liter per day. And again you have to convert the liter to meter cube. So 1 meter cube is equal to 10 power 3 liters. So solve this one, liter will get cancelled, meter cube will get cancelled. So you will obtain the value in per day. Okay, oh sorry, it is 1 by D, so it goes about days. So the retention time is calculated in days, which is nothing but 0.125 days. Okay, so this is about the activated sludge process. HRT is equal to V by Q. That is what you have to keep in mind. Now, the next is also about the activated sludge process. So here, completely mixed activated sludge process is to be used to treat the wastewater flow of 510 meter cube per hour. The flow rate is Q is equal to 510 meter cube per hour. Having the soluble BOD, BOD 5 is 240 mg per liter. The concentration of soluble BOD 5 escaping the treatment is. So after the treatment, how much BOD is escaping means, so before treatment in the wastewater 240 mg per liter is there. Okay. After treatment in the fresh water, that is the treated water, 11 mg is there. So we are talking about the BOD concentration. Now design criteria are all as follows, and the concentration of MLVESS is the amount of biomass is 2000 mg per liter. Now we have to compute the treatment efficiency of the process. What is the efficiency? Then it is very simple. Efficiency is equal to initial concentration minus final concentration divided by the initial concentration. Why it is S means? So S here means substrate because this contaminant in the wastewater is the substrate for the microorganism. Okay, so S naught minus SE divided by S naught. S naught is 240. Initially it is 240, finally it is 11 divided by 240. It is 0.9542. In terms of percentage, multiply it with 100. So it is 95.42 percentage. That is the efficiency of the ASP process. Okay. I hope it is clear. Any doubt in these two problems? Shall we move on to week 8? Now, week 8 is about the secondary process equipment again, advanced secondary process, and tertiary treatment is coming here. Okay, one more advanced secondary process is the microbial fuel cell. Okay, microbial cell, it can be a microbial fuel cell or microbial electrolysis cell, where the main focus is hydrogen production. Okay, so here we have the anode and cathode system. Okay, and the electron flow is like this. We have the electrolysis setup. Here the electrolyte will be there. That is a buffer solution is here to maintain the pH, to ensure the microorganisms are safe there. And then mainly you have a proton exchange membrane here. So what happens here is this proton exchange membrane will selectively allow the H plus ions alone. Okay. So this is how the hydrogen production is done with the help of microorganism coated in one of the electrode. Okay. And then this is one way of treating the wastewater. Okay. Here the microorganism take up the organic residues present in the wastewater and grow in number. And then in the tertiary treatment, so tertiary treatment is after the primary secondary. Mostly this tertiary treatment will reduce some amount of residual DOD, COD, and mainly it is focusing on the disinfection or cleaning of the treated water. Okay, so here you use adsorptive filtration. So many adsorbents will be used. Chemicals can be used. Adsorbent is nothing but there is a difference between absorption and adsorption. So if this is the solid matrix and the contaminants are getting absorbed means, so here within this matrix only the particles will be present. These particles or that is the contaminants are absorbed. Okay. So this is what absorption. And in the case of adsorption, there is a solid matrix. Okay. This is the solid matrix. So because of some physical or chemical interaction, your solid particles will be othered, that is adsorbed to the surface of the solid matrix. It is present over the matrix. Okay, this is the main difference between absorption and adsorption. So in the adsorptive filtration, they use the absorbents to remove the pollutants from the water. Okay. Now the next treatment method is the membrane separation. So membrane process is again you can use the membranes to remove the residual contaminants, and advanced oxidant process is mainly using the OH radical. Okay. This OH radical is produced by use of UVH2O2 or phenton oxidation process. Like this, many different methods are there to produce this hydroxyl radical. With the help of this radical, we'll be treating the water in the final stage. Okay, this is the overview of week 8, and this is the example problem. 100 ml solution containing 25 mg per liter of fluoride is treated with adsorbent doses, that is 5 gram per liter. The percentage removal of fluoride were given as 70%. Calculate the specific uptake. So initially, first we have a absorption column. Okay. So what is happening? 25 mg per liter. This is fluoride is the contaminant here. So for per liter of the wastewater, 25 mg of fluoride is there. Okay. When this wastewater is passed through this adsorbent matrix, finally 70% of the fluoride is removed. So 70% is removed, only 30% is passed on. So what is 70% of 25 mg? So you have to calculate 25 into 0.7. And here only 30% is remain. So 25 into 0.3. Okay. Calculate. This is the amount remaining. This is the amount removed. So 25 into 0.7 is 17.5. Okay. And 25 into zero point 0.3 is 7.5. So this much mg per liter of fluoride, this much mg of fluoride is there in 1 liter of the treated water after passing through the adsorbent column. Now, the question is the adsorbent used. So here, how much amount of adsorbent is there in this matrix? How much we are using means to treat 1 liter of water. Okay, we use 5 gram of adsorbent. Okay. Now our wastewater volume is, so the volume of wastewater is V is equal to 100 ml. For 1 liter of wastewater, we use 5 grams of adsorbent. So for 100 ml, we use only 0.5 gram of adsorbent to treat the 100 ml of wastewater. Okay. So this much concentration is left out for 1 liter. Then if the wastewater volume is 100 ml, divided with 100, and again here also divided with 100. So finally it is 1.75. 1.75 mg is absorbed by the adsorbent for the 100 ml of the wastewater. So if removed, fluoride removed by the adsorbent is 1.75 mg, and the amount of adsorbent used is 0.5 gram. So to calculate the specific uptake, we have to divide the F removed by the adsorbent divided by the amount of adsorbent used. So 1.75 divided by 0.5 is nothing but 3.5 mg per gram of the adsorbent used. This much amount of fluoride is absorbed by the adsorbent. So this is the specific uptake. Okay, I hope it is clear. Now the next problem is find the water flow rate in meter cube per meter square day when it passed through the porous polyethylene membrane. So it is a membrane filtration. In a membrane, how the filtration is happening in general means due to the pressure difference. Okay. So the differential pressure is 70 degree Celsius. Sorry, at the temperature of 70 degrees Celsius, because of the differential pressure, this water is passing through, and then the membrane has the porosity. So the membrane porosity, how much amount of pores are there in the membrane means 30 percentage, and then the diameter of the pore is 0.5 micrometer, then the tortuosity is 2. Okay. Then the pressure on either side of the membrane is 400 kilopascal and 100 kilopascal. Because of the pressure difference only, the water is flowing through. Assume the membrane is 2 micron thick and the flow is fully developed laminar flow. At 70 degrees Celsius, the data of water parameter are given. So the viscosity is 0.42 cp, and the row density is 1000 kg per meter cube. So the question is to find the flow rate of the water, which is nothing but Q, but it is asked to be found in the unit meter cube per meter square. So flow rate is meter cube and the area is meter square. So you have to calculate the Q in the terms of meter cube per day and the meter square. So you have to calculate Q by A. So we know that for a laminar flow, this is the constant formula. Q by AM is equal to epsilon d square into P naught minus PL divided by 32 mu Lm tau. So here this epsilon is the porosity, which is nothing but 30 percentage. So 30 by 100 is 0.3. And diameter D is given as 0.5 micron. So 5 into 10 power minus 6 meter square, whole square. And the pressure difference is 4 lakh minus 1 lakh pascal whole divided by 32. Mu viscosity is 0.42 into 10 power minus 3. And then Lm is again given. So thickness of the membrane is 2 micron. So 2 into 10 power minus 6 meter, and tau is given as 2. Okay. So this is in per second unit, because this is in Pascal, right? So Pascal is kg per meter per second. So you are converting the seconds to days. So to convert it to day, so in a day there are 24 hours, and in a hour there is 60 minutes, and in a minute there is 60 seconds. So 60 into 60 is 3600 into 24. Then you will obtain the Q by A in terms of day. Okay, to solve this, you will obtain 36,160.71 meter cube per meter square day. I hope it is clear. Is there any doubt? Discharge Q is calculated in meter cube per second. Okay. Q unit of Q is meter cube per day. Okay. And area is meter square. Since the flow rate is asked in this unit, we are calculating Q by A instead of Q. Okay. How this is calculated in day means this is converted, the second is converted to days by multiplying with 3624. In the question itself, it is asked in meter cube per meter square day. That's why we are calculating it. Volume is meter cube. Which volume? This question only you are asking. Okay. What is your doubt exactly? Why we are calculating meter cube per meter square day instead of meter cube per second? Is it your doubt? Yes. Because in the question itself, it is asked in this unit particularly. Okay, that's why we are doing all these calculations. Because the area is also not given, right? If the area is given, you can substitute the A value here and we can obtain the Q value in terms of meter cube per day or meter cube per second itself. Okay, if no unit is given here. And area is also unknown, and the question itself it is asked to calculate in meter cube per meter square day. That's why we are calculating in this term. Okay, it is nothing but the flow rate per unit area instead of just the flow rate. Okay. So now we will move on to the week 9 lecture. So week 9 is about the sludge management. So here, after all the process, we have the primary sludge, secondary sludge, and tertiary sludge. We have a sludge from different processes. Okay, all these sludge will be composed of both solid and liquid content. So if you take any sludge from any step, it is having both the solid and moisture content in it. So why the sludge treatment is important means these sludge can be incinerated after dewatering and drying. This can be incinerated, like it can be burnt, or it can be landfilled. It can be filled into the land, or it can be again treated with the help of the organisms like earthworms or microorganisms. We can treat them and we can dispose them in the terms of compost that can be used for composting process. Okay, there are different methods of sludge management. And then in the anaerobic digestion, we know that biogas is produced. Okay, for the biogas production, we have different type of anaerobic digesters. Okay, this is the introduction about the sludge management. And then we have industrial pollution control in GP1. So first we have seen about the sugar industry as example. So in the sugar industry, what is our ultimate product? Here we are producing the sugars from it, right? So now here the main aim is to produce the sugar. But whenever one product is formed, lot of pollutants are there. Like after taking the sugar, lot of byproducts from it, which includes the solid waste, and then we use lot of water in the treatment. So lot of waste water is also produced. So solid waste is there, and waste water is there. And then during the process, noise pollution will also happen. So this is also happening. Okay, so a lot of pollution is happening in different forms in from each and every step. How we can control the emission of the solid and liquid pollutants from the each treatment process is discussed in this sugar industry as an example. Okay, So we will see some problems. Find the specific gravity of sludge if it contains 70% volatile solid with specific gravity 1.7 and non-volatile specific gravity is 2.7. So specific gravity of volatile and non-volatile solids are given and the moisture content of the sludge is 98%. First, the formula is to find the specific gravity of sludge. The formula is 100 by specific gravity of sludge is equal to percentage of solid divided by specific gravity of solid plus percentage of water divided by the specific gravity of water. So now we know the specific gravity of water is 1, it is constant, and the percentage of water in it is 98. Okay, it is 98 percentage moisture. So the remaining 2 percentage is the solid, but we don't know the specific gravity of solid. Okay, it is always in the range of 2 only. Okay, the specific gravity of solid can be obtained by calculating calculating this one. We know that two different solids are there, volatile and non-volatile, and its percentage is given. So 70 by its respective specific gravity is 1.7 plus 30 divided by the respective specific gravity is 2.7. So the specific gravity of solid is 1.92. Just substitute this value here, you will obtain the specific gravity of sludge. Okay, this is a simple problem. Here, the specific gravity of solid is not given, so you have to find it from the given data. Now you have another question, which is a sedimentation tank is treating 5 mld of sewage containing 290 ppm of suspended solid. The tank removes 60% of the suspended solid. Calculate the weight of the sludge produced per day, assuming the moisture content of the sludge is 90%. So the flow rate Q is given as 5 mld, which is 5 into 10 power 6 liters per day. And the concentration of the solid is 290 ppm. 1 ppm is equal to 1 mg per liter, so 290 mg per liter. And then the efficiency is given as 60%. So the tank removes 60% of the suspended solid. And one more data given is the weight of the sludge produced, calculate the weight of the sludge produced per day, assuming the moisture content is 90%. So the moisture content is 90%. So now in this one, the tank is removing the suspended solids, which is 60%. The remaining only is going to be produced as the sludge. So the concentration of solid produced as the sludge is 60 by 100 into 290, which is nothing but 174 mg per liter. Out of 290 ppm, only 174 ppm is produced as the sludge. Others are not treated. Okay. So in this 174 mg per liter, we need to calculate the weight of the sludge. To calculate the weight of the sludge, first we need to find the total amount of solid produced. This is for 290 mg per liter, 174 mg per liter is there. But the capacity of tank is, it is treating 5 ml. Okay, so just multiply 5 with it. So if you multiply it with 5, there is a unit conversion happening here. So it is 5 into 10 power 6 liter per day. And this is 174 mg per day. Okay. Sorry, mg per liter. Liter will get cancelled. And again, here we have to convert this mg to kg. Okay. So that only you are obtaining this value in terms of 870 kg per day. And then one more thing given is in this one, this is the total mass of solid produced in this sludge. But the mass of sludge produced per day is, we have to calculate only the mass of sludge, that is the solid matter content. In the question itself it is given, it is containing 90% of moisture. So only 10% is the sludge content, remaining 90 is the moisture content. So this is the formula you have to use, which is nothing but 100 divided by 100 minus P. P is the amount of moisture percentage, which is 90 into 870, you will obtain 8700 kg per day. This is the total mass of the sludge produced in a day. First, you have to calculate what is the concentration of solid being produced as sludge and what is the total amount of sludge produced with the help of flow rate and what is the actual mass of the sludge alone instead of calculating the moisture content also, we have to subtract. So actual mass of the sludge is calculated with this formula. Okay. So the answer is 8,700 kg per day. Any doubt in that one? Is it okay? Okay, no doubts. Now we will move on to week 10. Recently only we have seen this week 10. I will brief it in a simple way. So this week 10 is about the pollution control in different industries like distillery. So distillery is where ethanol is formed, C2H64. When ethanol is produced, we are producing lot of wastewater in it, and other type of pollutants is also released from the ethanol production. That is what is discussed here. In the tannery, so tannery is nothing but using the skins and hides of the animal, we are producing the leather with the help of tannins. So tannin is a chemical compound. Initially we used the natural tannin, but nowadays we are using the chromium for the tanning process, which is the conversion of the animal skins into the leather. So this chromium is discharged into the water, used for the treatment in the each and every step. So removal of the chromium is very important. That is what discussed in this one, and how the sludge produced are all managed or discussed earlier. Now coming to the petroleum refinery, from the crude oil, we produce a lot of valuable products like LPG, butane, gas, like that many products are produced from the petroleum based products are produced from the crude oil in the petroleum refinery. In the case of petrochemical industry, using the petroleum product, we form some usable form of product. Okay, some other products are also produced in the petrochemical industry. In both of these industries, we use lot of water and lot of gaseous emission will also happen in between. How to control these one we have seen in this lecture. Now coming to the last lecture of week 10, it is dealing about paper industry. So in the pulp and paper industry, again we use a lot of water. It's a very water intensive process. In the fertilizer industry, we produce urea, diammonium phosphate, and then superphosphate. All these are produced. So for that also we use a lot of amount of water. Okay. And then in the copper smelter industry, we use different types of ore. We have the oxide ore and we have the sulfide ore. If it is oxide ore, then the contamination is very less. If it is sulfur containing ore, it is a sulfide ore means then there is a lot of removal of sulfur. Okay, so this will be affecting the air quality. This is what discussed in all these industrial pollution control. So this is one of the example problem in the biogas production. The question is in an industrial, I have two representative problems for this week 10 lecture. Shall I continue it? If you want, I will continue. It's 110. Okay. So this is this week problem. Sorry, week 10, last week problem. In an industrial biogas plant, food waste is anaerobically digested to produce the biogas. The slurry contains 10% of solid food grain. The elemental composition of the food grain on the dry basis is CHON. Okay, around 90% of the food grains are converted to biogas. All are converted to hydrogen forms. All of the converted hydrogen forms the methane. If the flow rate of the slurry is 3,500 liter per day, calculate the rate of biogas. That is the amount of CO2 and CH4 produced. Okay, the question is very simple. We have the plant food waste. Okay, in the biogas plant we have the food waste. Okay, so this food waste is having the solid grain of only 10%. In this food waste, the slurry contains only 10% of solid. Okay. And this food waste composition is CHON based upon the mass. So if we add everything, we will get 100%. So in mass percentage, the composition of CHO and N is given for the food grains, and this food grain is only 10% of the food grain is formed into the is the solid food grain. Okay, 10% of the food grain is only formed as the slurry. Now, to find the amount of biogas produced, we will see the step-by-step solution. The flow rate of the slurry is 3,500 liter. Okay, it is given in the question itself. And the dry solid food grain used is out of this 3,500 liter, only 10% of the solid is there. So into zero point 0.1 is 350 kg. This is the dry solid of food grain totally used for the biogas production. Now assume the density of the slurry as 1 kg per liter. That's why this 3,500 liter is converted to 350 kg. Instead of liter, we have used it as kg. Assuming the density is 1 kg per liter. That is nothing but 1 liter is equal to 1 kg. Okay. Now the CHON composition are all given, which is 55, 35 and 10% respectively. You know that 350 kg is the dry solid food grain used for biogas production. In the 350 kg, 50% is your carbon. So the total amount of carbon is 175 kg. And in the 350 kg, 5% is your hydrogen. So the total amount of hydrogen is 17.5 kg. And in the 350 kg, 35% is oxygen, it is 122.5 kg, and nitrogen content is 35 kg. Okay, this is how you have calculated the respective weight portion of CHON in the 350 kgs. Okay, so out of this CHON, what is our product? Methane and carbon dioxide. Okay, one of the data given, one clue given in the question is all the hydrogens are converted to methane. Whatever the hydrogen is present here is completely converted into methane. Okay, so 17.5 kg of hydrogen is used for the methane production itself. It is given. Okay, and one more data given is around 90% of the food grain are converted to biogas. So this is for 100% of the food grain, this much composition is there for CHON. But out of this 100%, that is out of 175 kg of carbon, only 90% is converted to carbon dioxide and methane. So 90% of 175 is 157.5 and 90% of hydrogen is 17.5 into 0.9, 15.75. So how much kg of hydrogen used for methane production means 15.75 kg is used for methane production. We know that the molecular weight of methane is 16, right? So if you take 16 kg of methane, you require 4 kg of, this is just a stoichiometric balance. You require 4 kg of hydrogen to produce 16 kg of methane. Now, they have given a clue that all the hydrogen is converted to methane only. So, for 15.75 kg of methane, 15 point, yes, it is correct. So, for the 15.75 kg of methane, how much kg of hydrogen, how much kg of methane is produced? Just multiply it to find the unknown. So 16 by 4 into 15.75 is 63 kg. This much amount of methane is produced now. Now the carbon used for methane can be easily calculated. Again, this is a hydrogen balance. Now for the carbon balance, for 16 kg of methane production, how much kg of carbon is used? The atomic weight of carbon is 12. So 12 kg of carbon is used. Since you know the amount of methane produced, which is nothing but 63 kg. Okay. So 16 kg, you require 12 kg carbon. For 63 kg, you require how much amount of carbon? Just cross multiply this one. So you will obtain 47.25 kg. So this is the amount of carbon used for the methane production. You know the total amount of carbon used converted into biogas, which is 157.5. Subtract these two, you will obtain the amount of carbon present as the carbon dioxide production. Okay. So in this 110.25 kg, this amount of carbon is used for the carbon dioxide production. So now again do the stoichiometric balance for CO2. So 44 is the molecular weight. To produce the 44 kg of CO2, you require 12 kg of carbon. Okay. Now you used 110.25 kg. So 110.25 kg is used for the carbon dioxide production. So how much amount of I think I have made some mistake. I'll just write it. So 12 kg of carbon is used for 44 kg of carbon dioxide production. If you use 110.25 kg, how much amount of carbon dioxide is produced means 404.25 kg. Okay. Now we have found the CO2 and CH4 produced. Just add these two to find the total amount of biogas produced in the biogas plant. It is 467.25 kg. Okay. Any doubt in this one? Any doubt? Shall I move on? So, the last problem of today's session is the flow rate of wastewater from tannery industry is 2 kiloliter per day, and it has the chromium content of 15 mg per liter. As per the CPCB standard, the effluent should not contain total chromium as more than 2 mg per liter. Find the rate of chromium removal in gram per day required in ETP. If 90% of this chromium is recovered, how much MgO will be required for this recovery of chromium if stoichiometric conversion takes place? Okay. It's very simple. To solve this one, we should have the background idea what is happening in the tannery process. So in the tannery industry, you use a lot of water. Okay, you use a lot of water. So after the treatment process, the wastewater is produced. This wastewater is further classified into two types. One is the chrome based water, another one is the non-chrome based water. Okay. From each step, we have different steps in the tannery treatment. Okay. And we have tanning in between. So in the tanning only, you will use the chromium. Okay. For tanning process. Before that, you will not use any chromium. So those water are coming under the category non-chrome based water treatment. And whatever is coming after the step tanning process will have the chromium content. Those will be treated in the chromium based treatment tank. Okay. So how this chromium based chrome treatment is happening means they use two component. One is the MgO, which is the magnesium oxide, and another one is the sulfuric acid. Okay. By using this only, the chromium is recovered and only the non-chrome wastewater is again sent to the non-chrome treatment method. So totally this non-chrome treatment method is again treated with the secondary treatment process like activated sludge process. Then secondary clarifier will be there. Then there will be the tertiary treatment, disinfection, filter treatments will be there in the tertiary treatment, like reverse osmosis, before that ultrafiltration, ACF filtration, activated carbon filter. So these many filtration will happen in the tertiary treatment. Finally, the clean water will be sent out. Okay, this is the theory behind this question. Now, with this introduction, the influent chromium concentration in the treatment tank, the influent chromium concentration is 15 mg per liter. That is what given here. And the effluent chromium concentration is, there is a limit that it should not be more than 2 mg per liter. The flow rate of the water is given as 2 kiloliters per day. Now, to find the rate of chromium removal, it is very easy. Rate of removal is 15 minus 2. 13 mg per liter is removed, but the flow rate is 2 kiloliters. That is 2000 mg per day. Okay, this this is 2000 liters per day. Here it is mg per liter. So it gets cancelled. So you'll obtain mg per day. This is the total amount of chromium removed in a day. That is 26 grams per day. Okay. How much amount of chromium is recovered means 90% is recovered. Okay. 90% is recovered means 23.4 gram per day is recovered. Okay. Remaining only is not recovered. So the question is to find the rate of chromium removal in a day. The first part is over. Next part is, if 90% is recovered, how much MgO is used? We have to calculate the amount of MgO. So initially I have found the amount of chromium recovered, but you should use the stoichiometric balance to find the amount of MgO used, because this chromium is supplied in the form of chromium sulfate for the treatment. Finally, it produces the chromium. You have to use the MgO, okay, which is nothing but magnesium oxide, to remove the chromium sulfate, and then it produces the magnesium sulfate and chromium hydroxide finally. Okay, this is the stoichiometric balance. Like this is the molecular weight of chromium sulfate, which is nothing but 392 grams. Okay, this is 3 into 40 is 120 gram is the molecular weight of magnesium oxide. That is, for every 392 gram of chromium sulfate, to capture this chromium sulfate, you require 120 grams of magnesium oxide. Okay. Now you know that you have the chromium of 23.4 grams, right? For 392 grams, 120 grams is required. For 23.4 gram, uh, this is the 23.4 gram is the amount of chromium. Now we have to calculate the amount of chromium sulfate. So the weight of the chromium is 104. Molecular weight is Cr2 plus is Cr2 is now Cr2 SO4 thrice is 392. Okay. So convert the chromium to chromium sulfate. If 23.4 grams of chromium is recovered, how much amount in terms of chromium sulfate recovered means 88.2 grams. Now 392 grams of chromium sulfate requires 120 grams of magnesium oxide. So 88.2 grams of chromium sulfate requires how much amount of magnesium oxide? That is what you have to find. So 120 into 88.2 divided by 392 is 27 gram. So this much amount of magnesium oxide is required in a day to remove the chromium in the form of chromium sulfate. Okay, is that clear? Any doubt? Okay. Okay. This is the end of the session. Thank you. Thank you for joining the today's session. Then for the next 2 week lecture, join the upcoming Thursday classes from 3 p.m. to 5 p.m. I will be taking the session. Thank you for joining today.